Welcome to the debate. You know, when you build a physical machine, say a high-speed train, the emergency brake is basically just a physical steel cable. You pull it, the brake pads clamp down, and the train stops.
Right. It's just Newtonian physics.
Exactly. It is guaranteed. But now I want you to imagine if that emergency brake wasn't a steel cable, but a statistical probability.
Oh boy.
Right? You pull the lever in a panic, and instead of clamping down, a neural network calculates a 99.8% chance that stopping is the optimal action. Meanwhile, it's simultaneously considering if maybe just slowing down is slightly better for passenger comfort based on real-time telemetry from the tracks.
Which sounds incredibly dangerous if you happen to be, the person standing on those tracks waiting for the train to stop.
Precisely. And that is exactly the transition modern engineering is facing right now. We are taking autonomous AI agents and deploying them into our most critical infrastructure. We're talking about power grid management, automated cyber defense, and industrial SCADA systems for water treatment.
Algorithmic financial trading networks. Yeah.
Yes, exactly. All of it. And so today, we're debating the tension between operational efficiency and the absolute necessity for rigorous human controls. As these systems transition from enterprise productivity tools to physical execution, an unconstrained action doesn't just mean a typo in an email anymore.
No, not at all. A hallucinated response could lead to rolling service blackouts, market flash crashes, or catastrophic physical damage to industrial hardware. The stakes for systems engineers and operators are just fundamentally entirely different now.
They really are. So my position today is this. In critical systems, deterministic safety layers and strict human-in-the-loop escalation must take absolute precedence over operational efficiency to prevent systemic failure. A human has to hold that steel cable.
And I look at that exact same infrastructure and see a totally different reality. My position is that relying on manual human oversight creates fatal operational bottlenecks. And true safety in high-stakes environments actually requires replacing humans with self-executing policy engines and mathematical state verification.
Okay, well, let's talk about the reality of how these models function. I call this the non-determinism dilemma.
Okay.
When you integrate a statistical machine learning model into a safety-critical framework, you are basically violating the core assumptions of traditional software engineering.
Because of the probabilistic nature of the model?
Exactly. Traditional safety engineering relies on systems acting the exact same way every single time. But neural planners are inherently probabilistic. If you give an AI agent the exact same environmental inputs on Tuesday that you gave it on Monday, it might yield a completely different action proposal.
Right, because it's sampling from a distribution of possible outputs. It isn't just a simple lookup table.
Right. And because of that, we cannot rely on open-ended tool execution. We have to wrap these reasoning engines in deterministic guardrails. We need circuit breakers. If telemetry indicates anomalous state drift, or if the model's confidence drops, the system must fall back to classical algorithmic control and trigger an immediate human escalation. The machine just cannot be trusted to grade its own homework when the variables change.
I mean, I understand the instinct there. We all want a human to step in when things look scary. But I think you're ignoring the control-utility trade-off. We are deploying these agents specifically because human cognitive bandwidth is already maxed out.
But at what cost?
Well, look at it this way. If an autonomous agent has to pause its workflow and prompt a human supervisor for every third subtask just to be safe, you've completely negated its primary capability. You haven't built an autonomous agent. You've just built a very expensive, very complicated manual notification system.
But wait, isn't a notification system exactly what you want when a nuclear reactor or a power grid starts acting erratically?
Not if the notification system is what causes the failure. I mean, mandatory human-in-the-loop requirements create severe operational bottlenecks. Think about it from the operator's perspective. It leads directly to a really dangerous psychological phenomenon known as approval fatigue.
Okay, sure. Alert fatigue is real.
It's more than real, it's systemic. If you put an operator in a security operations center and make them click approve on 500 minor automated actions a day, by Friday afternoon, they are just blindly clicking yes to get the queue down. They aren't providing oversight. They are just a rubber stamp. Human oversight is simply too slow for domains like automated incident response.
Okay. Both of us clearly recognize that the failure states here are catastrophic, but we are deeply divided on who or what is best equipped to handle real-time crisis intervention. You're arguing humans are a bottleneck. I argue they are the only reliable circuit breaker.
Let's unpack why that human bottleneck is so dangerous, especially in multi-agent environments. Think about a multi-agent cyber defense system in a modern data center. You aren't just dealing with one AI making one isolated decision.
Right, there are dozens of them.
Exactly. You have complex feedback loops that create emergent swarm dynamics. Human operators cannot mentally model, let alone react fast enough to those unpredictable swarm dynamics.
Give me a concrete example of what that looks like in practice.
Sure. Imagine this. A cyber defense AI sees a massive, unexpected traffic spike on a server, so it isolates the server to protect the network.
Makes sense.
Right. But immediately, a second AI sees the first server go down, assumes it's a hardware failure, and aggressively reroutes all traffic to a backup cluster. Then a third AI sees this massive sudden reroute of internal traffic, misinterprets it as a coordinated insider DDoS attack, and begins shedding load by literally unplugging systems.
Wow.
That entire chain reaction, that emergent swarm dynamic, happened in 0.2 seconds. A human operator just blinked and the entire data center is offline. By the time the human understands the state of the board is changed 50 times over.
Okay, that is a terrifying scenario. I will absolutely grant you that.
But your solution is essentially to trust the swarm to fix the swarm?
I'm saying the execution latency introduced by human approval is just as catastrophic as a bad AI decision. But you are assuming the system is operating within a paradigm it fundamentally understands, even if it's moving at light speed. What happens when we face entirely novel attack vectors?
You're saying the AI won't recognize an attack if it hasn't seen it before?
Exactly. I call it a distribution shift. Take the Texas energy grid failure a few years back. Let's say an AI agent is balancing the load based on predictive telemetry. Suddenly, an unprecedented extreme weather event hits a localized deep freeze that the model's training data has literally never accounted for.
Right, the physical parameters change.
The parameters change because ice is freezing the wind turbines. In these edge case scenarios, neural networks don't just fail, they fail with high confidence.
They hallucinate.
Yes, but they don't just hallucinate a weird word in a poem. They produce uncalibrated operational hallucinations. The AI proposes actions that look mathematically sound to its internal logic, but in physical reality, they're destructive.
Well, let me just finish this thought. Expecting an automated guard agent to govern an operational agent during an unprecedented edge case is like asking a student to grade their own exam when neither has learned the new material. You need a human operator who operates entirely outside the machine's localized logic. A human looks out the window, sees the ice, recognizes the absurdity of the AI's output, and pulls that physical emergency brake.
That's a very vivid picture, but honestly, human intuition is exactly what I want to avoid. That uncalibrated hallucination during a freeze is exactly why I advocate for mathematical state verification rather than human panic.
Human panic, yes. Humans misread telemetry under stress. Humans forget standard operating procedures when alarms are blaring in a control room. Mathematics does not. I agree with you that determinism is essential, but it absolutely does not require a human looking out a window.
I'm just not convinced by that because you can't wave a magic wand and mandate safety in a neural network. Look at traditional safety engineering. Take the DO 178 standard in aviation software.
Right, the flight control standards.
Yeah, that standard requires strict, deterministic software verification. Every single line of code must be traceable to a specific requirement, and its execution path must be exhaustively testable. You can trace the exact logic gate that says deploy landing gear.
Which, of course, you cannot do with a neural network.
Right. A neural network is just billions of continuous mathematical weights in a high-dimensional vector space. There's no single line of code to test. So to achieve anything resembling critical safety, engineers must enforce hard-coded policy layers that physically override neural decisions.
And I agree with the need for hard-coded overrides.
But if an AI agent wants to push a power grid transformer past its physical thermal thresholds, The classical control layer has to say no. And for this to be valid, you must have immutable audit trails of the AI's intermediate chain of thought reasoning. If a human isn't in the loop during the execution, they must at least be able to reconstruct the exact failure path afterward to adjust the hard-coded policy.
But you're still placing the primary burden on human review. Engineers don't need a human to read a log file. They can utilize state verifiers. Think of satisfiability modulo theories or SMT solvers.
Okay, SMT solvers are incredibly dense. How would you explain that to someone who isn't a systems architect?
Think of an SMT solver as an impenetrable mathematical fence. Before the AI's proposed command ever reaches the physical power grid, this solver runs a real-time mathematical proof. If the AI's command results in a physical temperature calculation above, say, 200 degrees, the math literally won't compute.
It bounds the action.
Exactly. The solver proves the action violates the boundary, and the action is killed instantly. The AI doesn't need to understand safety, it's trapped in a math equation. It's a closed-loop, fail-safe framework.
I understand the theory of the math fence, I really do. But there's a massive physical constraint you're ignoring. Running an SMT solver alongside a massive language model requires immense compute. You're assuming infinite bandwidth and unlimited server racks. But what about the physical realities of edge execution?
You're talking about swap constraints, size, weight, and power budgets.
Exactly. Swap budgets dictate reality in the field. In aerospace, defense, or even remote industrial mining, you might have autonomous systems operating in jammed environments. You don't have the luxury of phoning home to a massive cloud API to run your SMT solver.
Sure.
And you certainly don't have the bandwidth to send a telemetry dashboard to a human supervisor sitting in a bunker 5,000 miles away.
Which is exactly why you use highly optimized small language models, SLMs.
But wait,
SLMs are even more prone to hallucination because they have fewer parameters.
Yes, but they are capable of fast, localized inference. You can't rely on cloud computing in a jammed airspace. It's like trying to call a supervisor for instructions while driving a car through a tunnel. The intelligence has to live entirely inside the car.
Okay.
And because it's inside the car, we use hardware-level sandboxing. We isolate the agent's code execution inside restricted micro-virtual machines or action capsules. They execute safely on their own, guided by those local deterministic bounding boxes. The human is completely irrelevant in that millisecond to millisecond execution loop because they physically cannot be reached anyway.
Okay, look, I will concede that in a highly constrained, air-gapped, SWAP environment like a deep-sea submersible, immediate human oversight is physically impossible.
Right.
But let's broaden the lens back to enterprise networks and civilian critical infrastructure, where 99% of this deployment is actually happening. If we systematically remove human operators from real-time execution in favor of automated sandboxes, we plunge ourselves straight into what I call the liability void.
Wait, the liability void is a legal problem, not an engineering one. The courts will figure that out.
It is deeply intertwined with engineering. Liability dictates system architecture. Think about it. Imagine an autonomous agent deployed in a financial trading network. It's operating independently, autonomously chaining 20 tool calls together.
Okay.
And it misinterprets a minor market fluctuation as a systemic crash, executes a massive liquidity defense protocol, and triggers an actual flash crash. Or an IT agent gets confused and triggers permanent data loss across a hospital's entire network.
Disastrous, obviously.
Disastrous. But who is responsible? Traditional product liability entirely breaks down here. Did the foundation model developer build a faulty reasoning engine? Did the platform provider offer unsafe API tools? Did the engineer write a faulty SMT solver? Or did the end user simply provide an ambiguous prompt? If a machine does it all itself in a black box, who takes the fall?
Which is exactly why you can't rely on the end user operator at a keyboard to be the single point of control. You're viewing control as a binary switch.
Enterprise security teams must maintain a binary switch. We have to architect this using non-human identities, or NHIs.
Let's define NHIs for the audience for a second.
Right. So if you assign an AI its own identity on a network, an NHI, It essentially gets a corporate credit card with a strict limit. You tie that identity to strict model context protocol scaffolds. You set hard financial or computational spending caps per execution loop.
So it runs out of budget.
Exactly. An agent only gets $10 or maybe 10,000 compute cycles before it hits a wall and stops. If it tries to execute 20,000 tool calls and burn through budget to solve a problem, the system cuts up the credit card. It's not about trusting the AI. It's about restricting its oxygen. Without a human explicitly authorizing the continuation of that chain, accountability is impossible.
I'm sorry, but I just don't buy that framework.
Why not?
Because you are still looking at control as something held by a single person. The liability void is solved by understanding how authority is fragmented across the system. Fragmented authority is how modern systems actually scale.
Fragmented authority usually means no authority at all when things go wrong. Everyone just points fingers at each other.
Not if it's architected correctly through cryptographic action verification. Look at the 4 operational layers we are building toward. Layer 1, the foundation model providers, the hyperscalers. They control the primary compute. If an agent violates core alignment, they can revoke API tokens instantly.
Okay, that's layer 1.
Layer 2, the enterprise deployers. The people setting those NHI boundaries and spending caps you just mentioned. Layer 3, sovereign regulators. This is crucial. Regulators enforce frameworks like the EU AI Act or NIST AI agent standards. They dictate mandatory conformity assessments for high-risk agents before they're ever turned on. And finally, layer 4 is the end user.
That is a lot of layers, but if an AI deletes a hospital's database, suing the hyperscaler who provided the API token won't recover the patient data. How does your fragmented authority actually solve the immediate real-world liability?
Because the solution to the liability void isn't forcing a human to approve every tool call, it's graduated autonomy models combined with cryptographic auditing.
Graduated autonomy, meaning the AI earns the right to operate without supervision?
Exactly. You systematically unlock higher capabilities only after an agent builds a verified track record in a sandboxed, mathematically verifiable operational space. But more importantly, every single action the agent takes, every database change, every transaction, every network reroute, must be signed with cryptographic action verification, using traceable, revocable keys.
So like a digital signature for every microaction?
Yes. If an agent executes a trade, it signs it cryptographically. When the dust settles, we don't have a black box. We know exactly which agent operating under which non-human identity, at what exact millisecond timestamp, authorized by which policy engine, executed the action. We have a mathematically undeniable audit trail. You don't need a human to hit approve if the mathematics of the authority chain are cryptographically guaranteed from start to finish.
Chains when the underlying policy engine evaluating them is itself AI-driven.
How do you mean?
Earlier, you mentioned automated guard agents monitoring operational agents. If you replace human oversight with a secondary AI designed to monitor the primary AI, you haven't solved the non-determinism dilemma. You are just pushing the non-determinism problem one layer deeper. It's turtles all the way down.
Well, only if the guard agent is using the same probabilistic logic, which, as I said with SMT solvers, it shouldn't be.
But the real world defies clean mathematical fences. If the operational agent finds a clever, unintended workaround to a policy, a loophole in the math fence, what makes you think the guard agent won't be fooled by the exact same adversarial logic?
Because the math boundary is absolute.
But the human mind brings a completely different cognitive architecture to the oversight process. We don't just process rules, we process context, intent, and common sense. If an AI suddenly decides the best way to balance the power grid is to shut off electricity to the entire eastern seaboard, a human operator immediately recognizes the contextual absurdity of that. Advanced reasoning engines still completely lack that kind of grounded, physical common sense.
Look, I hear the appeal of human common sense, I really do, but we also have to admit that humans bring fatigue, bias, and a cognitive processing speed that is about 1,000,000 times too slow for the systems we are discussing today.
We can't just engineer humans out of the loop because they're slow.
We can build mathematically sound state verifiers that don't rely on common sense precisely because they rely on absolute physical limits. If the temperature of the transformer exceeds X, action equals null. That doesn't require a guard agent to understand the context of an ice storm. It just requires a boundary check, a simple, undeniable mathematical fact.
I think this is the crux of it, isn't it? The tension between a system that can think fast and a system that can understand what it's actually thinking about. My position remains that the inherently probabilistic, non-deterministic nature of AI absolutely demands deterministic, human-in-the-loop fail-safes.
Right.
Whether it's an energy grid, a hospital network, or a financial market, when we're dealing with systems where failure means physical catastrophe or systemic contagion, we simply cannot blindly trust self-executing loops. We need hardcore circuit breakers, and we need human operators who can step in when the edge cases and the unpredictable distribution shifts inevitably occur.
And my perspective remains that clinging to those human approval loops destroys the very autonomous utility we're trying to harness. It causes dangerous approval fatigue and slows response times to an absolute crawl. True safety in modern critical infrastructure doesn't come from a human panicking at a dashboard during a crisis. It comes from mathematically proven bounds, cryptographic action verification, and self-executing policy engines that can respond at the speed of the machine.
Well, I will say, despite our deep disagreement on the role of the human operator in real-time execution, there is a vital point of convergence here that we both recognize.
Definitely.
Both of us firmly agree that the era of speculative execution, the kind of open-ended, free-form tool use we see in consumer chatbots, is entirely dead when it comes to critical infrastructure.
Absolutely. Throwing a raw, unconstrained large language model at an industrial SCADA system and asking it to do its best isn't innovation. It's engineering malpractice.
Exactly.
We both agree that the future requires a hybrid model of intelligence. We have to figure out how to combine the vast reasoning capabilities and adaptability of deep learning with the guaranteed predictability and formal logic of classical control theory.
The goal, ultimately, is certified autonomy. It's about developing multi-tier governance architectures and rigorous engineering protocols to ensure these systems operate within safe bounds. There is so much more to explore in the evolving standards of AI engineering and regulatory frameworks, and I'd encourage everyone listening to dive deeply into the source material on this. The math fences, the swap constraints, the liability paradigms. It is a fascinating frontier.
And a necessary one to explore, because these aren't just theoretical boardroom problems anymore. These systems are being coded and deployed into the wild today.
They are indeed. And it brings us right back to where we started. As we replace the physical steel cable of the emergency brake with highly complex, probabilistic neural architecture, we have to ask ourselves, when the train is hurtling toward the edge, who or what do we truly trust to pull the lever? Thank you for joining us.